Hello everyone. Today we're going to talk about probability. So I want to summarize what we've done so far. So far we've been talking about statistics. We've been talking about describing, summarizing, organizing, and interpreting a set of data. So we've looked at frequency distributions, we've looked at tables and charts, and we've looked at means and medians and modes and standard deviations. The numbers are adjectives. So we are giving meaning to the numbers. And we have to be careful with how we talk about the numbers because we can change the meaning of the numbers and then science gets us into trouble because we think, that every year since 1950, the number of children died by handguns has doubled every year. And that's not true. So statisticians are dealing with enormous data sets. So we use descriptive statistics to summarize and simplify information. I've said it before, and I'll say it again. If somebody tells me the mean, median, and mode, I have a picture in my head of what that data looks like. If somebody tells me about standard deviation, I know how wide or how narrow our distribution is, if it's fat or if it's tall and skinny. We can look at bar charts to see the distribution of our data, and then we can try to communicate what we see, the patterns in the data. And that's our job. That's what I want you to do as a statistics student. So the empirical world involves seeing, touching, tasting, and smelling, using our five senses. And what we generally do is we're going to be collecting data with surveys, usually. And we're going to use descriptive statistics to organize, summarize, and give meaning to that data that we're collecting. That's what we've been talking about so far. But we're not only interested in describing the world. Sometimes we want to talk about causality. We want to talk about X causes Y. We also want to talk about the relationship between a sample and a population. We collect a sample of 100 people, but we don't actually care about that 100 people. We care about the thousands of people in our population that we hope our sample represents. And statisticians want to be able to make predictions about the future. So what do? Well, we need to go from description to what's called inference. So how do we get to inference? Well, step one is to realize that our world is full of chance situations. A chance situation is where we are confronted with possibilities whose outcomes we do not know. We don't know what's going to happen. People call this uncertainty. People call this the unknown. If you are in the military, you might call it the fog of war. We have the information we have, but everything beyond that is in the fog of war. We don't know, if they're going to try to surprise us, if they have an ambush set up, if there's 20 people waiting for us or 500. That's all the fog of war, uncertainty. So we can't get rid of uncertainty and the unknown. It would be nice, but we can't get rid of it. So humans have developed a way of dealing with uncertainty and the unknown. How do we do it? Probability. Probability is an effective way of dealing with uncertainty and the unknown. It's an amazing human innovation. Probability gives us a meaningful numerical description of things we admit we do not know. Probability gives us information that we can act on, and probability attempts to understand what to expect from randomness. That's what probability theory does, and that's what we're going to focus on today. So, if you buy a lottery ticket, what are the chances that you will win? If you walk across a golf course, what are the chances you will be hit by lightning? I want to do a little disclaimer here. One of my friends in high school was actually hit by lightning on a golf course, and he died. If you bet on red in roulette, what are the chances you're going to win? If you buy stocks and bonds, what are the chances those investments will pay off? The idea here is that probability is all around us. It happens every day, and a lot of people use it. Here are some more chance situations. If you have a fever and other symptoms, what are the chances that you have a serious disease, especially in a COVID world? A hurricane is spotted off the East Coast. What are the chances it will cause great damage? What are the chances a child brought up by a drug addict will become a drug addict themselves? These are all chance situations where probability is all around us. What are the chances an email advertisement will lead to a sale? What are the chances you get cancer if you live near a garbage dump or near power lines? What are the chances of being unemployed if you attend an Ivy League university like Harvard or Princeton? What are the chances someone will drop out of college? These are all probabilistic chance situations. So I'm going to repeat it again. Probability is an effective way of dealing with uncertainty and the unknown. If you find a more effective and reliable way of dealing with uncertainty and the unknown, please let the scientific community know as soon as possible, because we need better answers. So why is probability effective? Well, everything is a random happening. An individual outcome of a trial is completely unknown. If I flip a coin, it could be heads, it could be tails. But, big but, very important but, if I repeat that trial, if I flip that coin many, many times, and I look at it in the aggregate, there is some regularity. So, again, we all know that if you flip a coin, the chance of a heads is 50%, the chance of a tails is 50%. But each individual flip, I have no idea. It's a guess. It could be heads, it could be tails. I don't know. It could be either one, right? But on the aggregate, I know that if I flip 100 coins, it's going to be roughly 50-50. If I flip 1,000 coins, it's going to be roughly speaking close to 50-50. It could be 480 to 520. It could be 440 to 560, but it's ballpark 50-50. So the amazing accomplishment of probability theory is that it articulates a meaningful numerical value on things we do not know for things in the aggregate. Probability tells us about the big picture. So when our outcomes are equally likely, we don't have what's called a normal curve. When we flip a coin, it's called a uniform distribution. Flipping a coin and rolling a dice are examples of chance situations where all outcomes are equally likely to occur. So the chance of flipping a coin is 50-50. If you have a six-sided die, you have a 1 in 6 chance of rolling a 1, a 1 in 6 chance of rolling a 2, a 1 in 6 chance of rolling a 3. Most patterns in the social world are not uniform distributions. They're not equally likely to occur, but there's some that are. Oh, okay. So here, let me make sure I didn't go too fast. Okay. So I want to explain probability to you. Here are the features. Probability is equal to a number. The number is always between 0 and 1. 1 means absolute certainty that it will happen. 0 means absolute certainty that it will not happen. Now, I know I just said that, but 1s and 0s are pretty rare in the world of probability theory. Unless you have something like a coin flip. 1 for heads, 0 for tails, so you can do that, will have 1s and 0s. But everything else, other than flipping coins, or what's called a binomial distribution, everything else usually is expressed as a fraction or a decimal. There was a great radio story one day that said we can calculate the probability that you're in, a country really far away and bumping into somebody in your hometown. And the idea is that it's never 0. The probability that you go to an airport in Nepal and you bump into somebody from your childhood is like 0.000001. Notice it's not a 0. There's always a probability that things are going to happen, right? So that's how probabilities are expressed. A 0.5 would mean there's a 50% chance of it happening. A 0.25 means that there's a 25% chance of something happening. It's basically decimals being turned into fractions or percentages. So I hope all of you are familiar with, the idea that a decimal can be turned into a fraction or a percent. So giving a numerical value to chance, that's what we're doing. We're giving a numerical value to a random process. So a 6-sided die, coming back to that example, there's a 1 in 6 chance of rolling a 5. The probability of rolling any side, if you figure out the math, is really 0.167. Here's our image of that. The chance of rolling a 1 is 0.167, 2, 0.167, 3, 0.167, 4, 0.167, 5, 0.167, 6, 0.167. That's the probability of rolling each side of the die. It's uniform. Now again, if we did this trial, and we did it 1,000 times, it's possible you might get slightly more 6s than the rest of them, or slightly more 3s than everything else. But on the whole, it's going to come pretty close to 0.167 for each one. So if you're rolling a die, it could be a 1, 2, 3, 4, 5, or 6 each time. The probability of each particular number is always 1 in 6. Is it possible to roll a 5 10 times in a row with a die? The answer is yes. Does this mean that probabilities are wrong? No. So here's the thing you really got to understand. This is a long-run, big picture idea. I could roll a die and get 10 5s in a row. But the question is, if I roll these dice 100 times, on the whole, big picture, I'm going to get 0.167, or pretty close to it, right? So I want to tell you a short story. When I first started teaching statistics, I was horrible at it. I didn't know what I was doing. So I told my wife, I said, I'm a horrible statistics teacher. So I went out and bought a statistics class by like the best statistics professor in the United States. He taught at the University of Texas. His name was Michael Starbird. And I watched him teach, and he tells a story that's really worth sharing. He would tell his students to go into groups and flip coins 200 times and write down the results. Head, tails, tails, heads, heads. And he'd tell them to go on another piece of paper and fabricate their data. He would tell them, you know what, right? Heads, tails, heads, tails, 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 heads. And then I want you to come to me and present me the 2 pieces of paper. The one where you wrote down the real coin flips that you did and recorded, and the data that you fabricated. And I'm going to tell you which one's real and which one's fake. So the students would do this in groups, then they'd bring him their paper, and he'd say, this one's fake, this one's real. And the students were always amazed at his ability to do it. And the thing that really helped him make the guess, because it was a guess, was students underestimated how many times a die would come up the same number over and over. Students would try to fake him out by putting heads, tails, heads, tails, heads, tails, like it was alternating every time. They'd be like heads, heads, tails, tails, heads, heads. But when they made up their data, they didn't like to put 6 heads in there and then 3 tails. They didn't like to put long runs of the same thing because they thought that would look fake. But it's actually the opposite. It happens. When you flip a coin, you roll a die, you will get 3 2s in a row. You will get 5 heads in a row if you flip a coin. And people think, oh, the probability is 50-50, so if I'm going to fabricate it, I should do heads, tails, heads, tails. But he actually looked for the runs of the same number over and over to tip him off. So, what are we doing? If we have an equally likely possible outcome, the chance of any one of the outcomes occurring over the total number of outcomes that are possible. That's how you state a probability. I really tongue-tied myself there. Let me try it again. So for a die, it's 1 out of 6. Why? There's 6 possible outcomes, and there's 1 outcome that we're looking for. So what's the probability of rolling a 1? 1 out of 6. What's the probability of rolling a 2? Well, there's 6 possible outcomes, 1 out of 6. So that's how you create a probability for something like a die roll. So let's look at something like cards. What are the chances of drawing a red card from a deck of playing cards? Well, I'm going to give you the answer here. There's red cards and there's black cards. There's 26 red cards, there's 26 black cards. There's 52 cards in a deck. So 26 red cards over 52 black cards, we reduce the fraction, and we're going to get 1 over 2. The chance of drawing a red card is about 50-50. every other card we'd guess would be red. Every other card would be black. Now, of course, you could draw a card and it's red, it's red, it's red. But over the long haul, if you pick the whole deck, you're going to get 50% red, 50% black. So the chances of each individual card, our best guess is 50%. Half of them red, half of them black. What are the chances of drawing a 10, jack, queen, or king? Well, if you're a blackjack player, again, we want to do our math. So we've got 4 tens, 4 jacks, 4 queens, 4 kings. 4 times 4 is 16. 16 out of 52, that's the probability. The chance of drawing a 10, jack, queen, or king is 16 over 52. We can again reduce the fraction. But that's a probability. What's the chances of drawing a 10 right off the top? 16 over 52, right? Okay, here's a trick question. It's a critical thinking question. You're betting on a dice roll. The previous 2 rolls were a 2. Someone says to you, I bet $20,000. The next roll is not a 2. Considering the fact that the previous 2 rolls were a 2, what's the probability that the next 2 rolls will be a 2 again? Now, we don't have to play with all the math on this, but what I'm trying to teach you is something called the gambler's fallacy. You see this all the time when you go to casinos. If you go with a friend, they'll see somebody roll something or they'll see something happen and they'll say, oh, well, it was just black, so the next one's got to be red. That is false. That's the gambler's fallacy. That's part of the gambler's fallacy. The idea is that each individual trial is independent. We don't know. If I roll 2 dice and I get a 7, what's the possibility of me rolling a 7 again? Well, it's 1 out of 6 with one die, 1 out of 6 with the other die. It doesn't change. If I roll a 7, the dice don't talk to each other and say, well, we were a 7 last time, so we can't be a 7 again. Every roll is the same probability. So just think about that. A lot of people have this false mentality that if it was red last time in roulette, the next time it's got to be black because it's a 50-50 chance. And the idea is no. Every single spin of the wheel in roulette, it could be red, it could be black. There's a 50-50% chance of each. And just because it was red last time doesn't mean it's going to be black the next time. It doesn't. Every chance is 50-50. So here we go. Most random variables in the social world are not equally likely to occur. Most variables in the social world are not uniform. Gender is one that's useful to think of like a coin flip. If you're going to hire somebody, you could hire a man, you could hire a woman. That's like a coin flip, right? But other than gender, most other things don't fit that what's called a binomial distribution. It's a more of a normal distribution. So most patterns in the social world have outcomes that are very likely to occur and outcomes that are very rare. So here are some examples of things that conform to what's called the normal curve. Height is normally distributed. Grades tend to be normally distributed. Many behaviors tend to be normally distributed. IQs tend to be normally distributed. Income is a little skewed, but it is more or less normally distributed. Sexual activity is normally distributed. A lot of drug use is normally distributed. So what we do as statisticians is we look at the social world and then we think about math. And we ask what mathematical model best fits the probabilities we see in the world. Again, men and women, 50-50 population, more or less, binomial distribution fits that. But if we're talking about height, if we're talking about IQs, if we're talking about income, we use this other distribution called the normal distribution. And there's other ones too. There's logarithmic distributions, there's the chi-squared distribution, there's lots of distributions. But the two I'm talking about right now are what's called uniform distributions, like the 50-50 one, and the normal distributions. If you take more advanced statistical classes, you will learn about other distributions. So what does the normal distribution look like? It looks like this. You see from the image that what's in the middle we would call normal or common. As you get out to the sides, you get uncommon, and then when you go really far out, you're now rare, okay? So people who are, drinking, 50 beers in a day, that's extremely rare. People who have one glass of wine at night, a little bit more common. People who have 0 glasses of alcohol at night are probably extremely common, right? But people who are drinking tons of alcohol are rare. People who have 0, absolutely like no sex at all, people who have a lot of sex, most people are somewhere in the middle, right? So that's the normal distribution. And a lot of things are normally distributed, and we're going to be looking at those things. So the normal distribution is bell-shaped, it's symmetrical, it's theoretical. It has a mean, median, and mode that are all coinciding at the peak, with frequencies gradually decreasing at the end of the curve. Again, it's a theoretical ideal. The real life never perfectly matches up. I want to just make a real important point here. Later in the semester, you're going to be looking at some real data, and I have seen students look at real data, and the distribution looks a little wonky, and they'll be like, oh, that's not normally distributed. It's got this little bump here. It's a little bit off to the left. And again, I want to tell you, the normal distribution is a theoretical ideal. When you're looking at real data, we kind of look at it and say, does it approximate a normal distribution? It's kind of like we might have an ideal of what love is, a platonic ideal of what love is, but all of us don't achieve that ideal love. We get pretty close, right? So that's what we're looking for, is pretty close. It's a theoretical ideal. We're just trying to get as close as possible. There is a point where you look at a distribution and you say, this is nowhere near the ideal. This looks like a totally different creature. It's not normally distributed at all. At that point, we say, yes, that is not a normal distribution. But I do want to warn you that many students, they're holding things up to this ideal, and nothing is ever going to fit the perfect ideal. This is an example of the perfect ideal. We have final grades in social statistics for 1,200 students from 1983 to 1993. This is fabricated data. You have these little stars on there to show you the shape of the distribution. One person got a 40, one person scored 100, and it looks like the median and mode and the mean are all in the 70s. So that's our perfect distribution. I mean, that's gorgeous. That is a perfect distribution, and I want to point out that this is fabricated data. This is not real data. So yes, this is a normal distribution, and we're looking for the shape of our distribution. This is a perfect shape, and we're also going to calculate the mean, median, and mode. If the mean, median, and mode are all exactly the same, you have a perfect distribution. In general, the mean, median, and mode will be off just slightly, because again, that's the ideal. So for this distribution, the mean was 70.07, the median was 70, the mode was 70. They're all essentially equal, so this is a normal distribution. And it also looked very symmetrical, right? The symmetrical one's the thing that a lot of people get caught up on. They're just like, look, it's not symmetrical, and it's like, it's symmetrical enough. It's pretty close. So the last thing we're going to end with is what's called area under the curve, which is how we can figure out probabilities. So everybody is under the curve. So the total area under the curve we could call 1. We could call it 1, we could call it 100%, we could call it the whole, but everyone's under the curve, so we're going to say the area under the curve equals 1. Well, the median is going to split our distribution in half. So half the people got below the mean, half the people are above the mean, right? What's the probability that you're above the mean? 50%. What's the probability you're below the mean? 50%. How much area is under the curve? Either 0.5 and 0.5, or we could say 50% and 50%. They're both, you can use both interchangeably, 50% or 0.5. This is where things get interesting. What if we go 1 standard deviation above the mean, 1 standard deviation below the mean? Well, we've got 68.25% of the people are going to be within 1 standard deviation of the mean. Now, you might be asking, hey Mike, how did you know that 68.25% of the distribution is within 1 standard deviation of the mean. And what I'm here to tell you is the reason why we learn to calculate standard deviations is because they're awesome. And if you have a normal distribution, on average, theoretically speaking, in the ideal world, if you go 1 standard deviation up and 1 standard deviation below, you're going to get 68.25% of the distribution within there. So I have a question for you that I'm going to put in your work for after class. What percentage is in that part of the curve? What percentage is in that part of the curve? That's going to be on your quiz. I want you to think about that. How do you figure that out? We have a symmetrical distribution, and we know 68.25% is here. How much is there? Next thing I want to tell you is that if we go 2 standard deviations above the mean, 2 standard deviations below the mean, we're going to have 95.46% of our data in that curve. What percentage is on the left little corner? What percentage is on the right little corner? Can you calculate that? And we're going to stop right there. I know that they're hard questions, but I want you to think about it and figure out what percentage are in those 2 corners. Okay, have a good day.